So this is going to be the fifth section of the eighth chapter of geometry, which is going to be on angles of elevation and depression. This is not going to be actually too much new here. It's basically going to be talking about a different kind of word problem than before. So we've been going over these triangle problems. This is going to be like a triangle problem that doesn't present itself as one right off the bat. So just a little bit of a new type of situation. So what are these angles of elevation and depression? So the angle of elevation and depression is simply what I put it as is how far you have to arc your head up to look at something, or how far you have to arc your head down to look at something. So let's say you're down here and a bird is up here. The amount of degrees you have to look up to see the bird is called the angle of elevation. So I'll put AOE, angle of elevation. The amount of arc the bird has to look down to see you is the angle of depression, AOD, angle of depression. These are always going to be equal. So if you have to lift your head 30 degrees up to see the bird, that means the bird has to lift its head 30 degrees down to see you from a baseline. So remember, you're always going from your baseline. So baseline looking straight across, same for the bird. Baseline looking straight across. Should probably put this up more towards the bird's head, but we'll deal with that. So angle, depression, elevation are always the same. It's just one is the degree of looking up, one is the degree of looking down. So let's look at some word problems involving these. So it says a crossbar of a goalpost is 10 feet high. A field goal attempt is made from 25 yards out. Clears the goal by 1 foot. What is the smallest angle of elevation which the ball could be kicked? Okay, so once again, draw a diagram, especially when you start these. So crossbar of a goalpost. So here's the goalpost. Here's the crossbar. Not the best drawing I know, but I'm no Picasso. It's 10 feet high. Whoops. So this is 10 feet high. 10. A field goal attempt is made 25 yards from the base. So here's the base of the goal post. 25 yards out is where the field goal attempt is made. So 25. And it says it clears the goal by 1 foot, which means that if it's kicked, it clears it by 1 foot. So from here to here is 1 foot. Okay? Clears it 1 foot up high from the goalpost. What is the smallest angle of elevation at which it could be kicked? So we want to know this angle right here. How far upwards does the ball need to be kicked in terms of angular degrees? I'll put a little theta here. Theta is kind of like our x for angles. It's just convention to use theta instead of x, but if you want to put an x down here, feel free. But we want to figure out how much of an arc angle-wise does this football need in order to get above the goalpost by 1 foot? Or again, if you're a football kicker and you know that this is going to be how it needs to go, how much of an angle do you need to kick at in order to make it go 1 foot above the goalpost, which is probably something you want to do, especially if it's an important game. So we do have kind of a triangle here, because remember this goalpost is at 90 degrees on the ground, because it's built on the ground. So if I redraw this into a more triangular format, my right angle here, my goalpost was 11 feet total. We have the 10 feet for the goalpost and then 1 more foot because the ball clears the goalpost. So 11 feet total for this height right here. That's how high up the ball needs to go at this point, is 11 feet high. That way it clears the 10 feet goalpost with 1 foot to go. It's going to start 25 yards out, 25 yards out. We don't know the distance it's going to travel diagonally, nor do we care. We simply want to know what the angle needs to be. How much of an angle does this kicker needs to kick at in order to make sure that this happens? Well, this looks something like a SOHCAHTOA problem, like from last video. SOHCAHTOA, SOHCAHTOA. So we look at this problem and we want to assess which one of these 3 situations can we work with, and then go with that. So in this case, I have an angle here. If I look, I have the opposite and I have the adjacent. So if I have the opposite and adjacent, that looks to be a tangent situation. So I'm going to say tangent of my missing angle, theta, or again, if you want to put x in here, that's fine, is equal to OA, opposite 11 over adjacent 25. Now, as we said before, if you want to solve for an angle, then you have to use the inverse function. So here I want to move the tangent over, but I want to keep the theta of the angle where it's at. So I'm going to take this side here and go tan inverse, and then over here, same thing, tan inverse. Because what this does is this cancels out. I'm left with theta. And then over here, I just plug this into my calculator. So go to my calculator, make sure I'm in degree mode, which I don't think I am. Nope. Make sure you're in degrees. And then we do tan inverse of 25. 11 over 25. which is 23.75. 23.75. So you have to kick it at a 23.75 degree angle in order to clear it 11 feet high, which would be 1 foot above where you need it to go. So again, if you're solving for an angle, you have to use the inverse trig operations to get the angle by itself. Most of these problems do revolve around a SOHCAHTOA situation. There are going to be some where you might be able to use Pythagorean theorem, but because you're going to be finding an angle in most of these, what's the angle of elevation, what's the angle of depression, most of the time you're going to be using SOHCAHTOA, and a lot of times you're going to be using the inverse functions. So remember, if you want to find an angle, inverse. If you want to find a side length, then you simply use the normal trig functions. And we'll have a few of those coming up here too, I think. But this is a very typical angle of elevation depression problem. So it's nothing different than what we did in the last video. It's just the word problem is given to us in sort of different format than just saying, here's a triangle, solve for it. So we have this situation here where a lifeguard is watching a beach. It says that the line of sight is 6 feet above ground. So that means that from the ground to the lifeguard, so from here to here, is 6 feet. And by converse, from here to here is also 6 feet, right? Because that's from ground to lifeguard's eye level. This is from ground to lifeguard's eye level. So these are both 6 feet, kind of like a big rectangle. She sees a swimmer at an angle of depression, of 8 degrees. So in this case, we know the angle of depression. The angle of depression is 8 degrees. This right here is 8 degrees. Okay? How far away is the swimmer from the tower? So we want to know how far is it from the swimmer to the lifeguard. So basically this red line right here. This right here, that's our x. We want to figure out how long that distance is here. So let me redraw this triangle over here just to make it a little bit cleaner. So this is my right angle right here. We know that the lifeguard is 6 feet above the water on their little tower over here, above the ground / water. We know that the angle right here is 8 degrees because they have to look their head down 8 degrees to see the swimmer. We want to know how much of a distance would the lifeguard have to cover in order to get to the swimmer if they started drowning or getting eaten by sharks or taken down by a squid or something like that. Well, again, this is a SOHCAHTOA problem. SOHCAHTOA. You do that so a little bit bigger there. So we want to figure out which one of these three situations do we have, and then go with that. So let's look at my angle here. Let's see what I know. I know the opposite, and I don't know the adjacent, but I know that's what I'm looking for. So this is the adjacent. So this looks like another tangent problem. Because I know the angle, I know the opposite, I simply want to know the adjacent. And the only one in here that has opposite and adjacent together is tangent. So it would be tangent of 8 degrees, because I know the angle this time, is equal to opposite over adjacent. Now, in this case, since my variable is on bottom, if you remember from last video, what I told you to do is basically swap the variable and the other side. So it'd be x is equal to 6 over tangent of 8. If you want to know why that is, look back in the last video. I'll tell you why. But that's basically what happens when the variable's on bottom. You take the variable, you take the tan of whatever, or sine of whatever, or cosine of whatever, and you switch them left and right. And then you simply plug this into your calculator. 6 divided by tangent of 8. So 6 divided by tangent of 8, not tan inverse, because we're finding a side here. Again, finding a side length means normal trig functions. 42.7 essentially. 42.7 feet. So they would have to swim / run 42.7 feet to get from where they are at to the swimmer should something happen, like, again, a shark attack or a squid attack or simple drowning or whatever. And so this is the second type of problem you have. Again, this problem and the last one are basically the two types of problems that you have in this section here. You have a problem where you're solving for the angle. You have a problem where you're solving for a side length. It's just that they're not given to you as typical triangle problems, so I'm running through this here so you can see kind of what to look for and what to construct. You have to construct the triangle yourself from the wording, whether it's modifying an existing diagram or drawing your own diagram like we did in this one. Let's try not this one here, actually, because this one's, if you want to try this one on your own, go ahead, but this one takes a little bit more time than what I want to talk about in a video, because these videos are meant to be kind of a focus point on the main idea here. So I'll save this for another time. If you want to try it, though, go ahead. It's actually not too complicated. It just takes a little bit more work. Let's do this one here to finish it out. So they want to build a ramp, find the length of the base of the ramp. So we already have a diagram here that's given to us. That's great. We know that the ramp is going to be 10 feet high. We know that the angle right here is 20 degrees. We want to know the length of the base, which means that we're probably going to want this line right here because that seems to be the base of the ramp. So I'll call that x. So once again, we need to figure out which one of our trig functions do we use. So ka or toa. Which one of these would best fit? Well, going from the angle that I know, which is the angle of elevation here, I know the opposite and I know the adjacent. Or I don't know the adjacent, but I want to find out the adjacent. So this is going to be another tangent one. You might be sensing a pattern here. Most of these problems involve tangent just because situations where you're given the hypotenuse in one of the legs or vice versa is kind of hard to say in terms of a word problem. It's not uh, insanely difficult, but it's just kind of awkward to phrase those problems sometimes. So a lot of times you have tangent situations, even though you can certainly have sine and cosine situations too. Um, so in this case, we'd have tangent of theta, which is 20, tangent of our angle, is equal to opposite over adjacent. And then once again, our variable's on bottom, so we switch x over here, 10 over tan of 20. And so we're going to go ahead and calculate that out. So 10 divided by tan of 20, get 27.5 essentially. The base has to be 27.5 feet long if you want to have a 20-degree angle of elevation and a 10-foot high. So again, this is what construction workers, carpenters, and stuff do all the time when they want to kind of blueprint or diagram what they're going to be going into. That way they make sure they have everything in the right proportions. Because if you try to make this 15 feet high for some reason, and you want an angle of elevation of 20 degrees, better be prepared for this to be bigger than 27.5 feet. So again, make sure you have all the right materials. So nothing to scoff at in this stuff. So that's the general idea here. Again, these problems shouldn't be that really new, shocking, new, hard content. It's just the wording's a little bit different, but the main concept's still there. SOHCAHTOA, just make sure that you draw a diagram or look at your diagram carefully to figure out which one of the SOHCAHTOAs that you have, and then go with that. And again, tangent's a popular one, so if you see yourself using that a lot in these problems, you're not mistaken. It's just a really popular one to use just because most situations lend themselves to be described easily using a tangent situation. So that's it for this video. Hopefully you enjoyed it. Have a good day, night, or afternoon.